Hello and welcome to this video on section 5.2, which is all about the definite integral. So let's remember from section 5.1 what we did. So in section 5.1, we were trying to estimate area under a curve. So if we have this curve here, we would try and guess this area under the curve. And the way we would do that is we would divide this interval into multiple subintervals. In this case, I have it divided into 1, 2, 3, 4 subintervals. And on each subinterval, we would draw a rectangle whose height was the value of the function at either the right endpoint, or possibly the left endpoint, or possibly the midpoint of the endpoints of the intervals. So in this case, I have 4 rectangles, and the height of each rectangle is the height of the function at the right endpoint. So we have this rectangle here, this rectangle here, this rectangle here, and then lastly this kind of flat rectangle here. And we would make these rectangles and we would use them to estimate the area under the curve. In section 5.2, what we're going to do is we're going to generalize this even more. All right, remember what we had here is each rectangle was an equal width. They were each 1 over n times the length of the interval. So like in this case, since we have 4 rectangles, we would take this entire interval, and each rectangle would have a base that's exactly 1/4 the length of this interval here that we care about. But what if the rectangles could have all different lengths? And what if we weren't forced to use the left endpoint, the right endpoint, or the midpoint? What if we could pick any point in the interval and evaluate the rectangle's height there? That's what 5.2 is about. And before we start talking about that, let me give us some definitions so we can all be on like an equal playing field. A partition P of size n is a choice of endpoints that divides a given interval from A to B into n subintervals, and they do not need to be of equal width. So basically, we just pick n points, n many points in this interval from A to B. The only stipulation is that our first endpoint, or our first point, x naught, has to be our left endpoint A, and our last point, xn, has to be our other endpoint B. That's the only stipulation. Okay? That's what a partition is. And I'm going to draw some examples to help us get a visual understanding of what this is in just a second. Once we have a partition, we can then pick sample points. Okay? Sample points are just a set of points where each of these C1, C2, etc., each of these belongs to the interval between xi minus 1 and xi. What do I mean by that? Well, what I mean is that C1 is some point that belongs to this interval between x0 and x1. C2 is some point that belongs to this interval between x1 and x2, etc. The length of the ith subinterval, so, if we have multiple subintervals, the length of a subinterval is just the right endpoint minus the left endpoint. Just xi minus xi minus 1. So it's just the right endpoint minus the left endpoint. Just the length of the subinterval. And then lastly, the norm of our partition P, denoted with these 2 vertical lines on either side, is the maximum length of the subintervals. Okay. Again, what does this mean? We'll look through a visual now. So right here, I have a function. The function is minus x cubed plus 3x squared. And I want to figure out the area under the curve between x equals 1, so that's this black line here, and x equals 3.25. That's this endpoint here. Okay, those are our endpoints you can see here. And what I'm about to do is I'm about to lay down our partition points. So I'm about to partition this interval from 1 to 3.25. That's this interval here. I'm about to partition it into multiple subintervals. And the way I do that is I essentially just throw down a bunch of points. I'm forced to choose this left endpoint and this right endpoint. That is chosen for me. I'm forced to choose that. Other than that, I can pick any points I want to. So I'll pick this point here at 1.25, this point here at 1.5, this point here at 2, and this point here at 2.4. So what I've done now is I've broken this larger interval from 1 to 3.25. I've broken it into 1, 2, 3, 4, 5 subintervals. So we have this interval from 1, 0 to 1.25. That's one of our subintervals. We have a subinterval from 1.25 to 1.5. We have a subinterval from 1.5 to 2. We have a subinterval from 2 to 2.4. And then our last subinterval is from 2.4 to 3.25. Okay, we can pick as many or as few partition points as we want. The only thing that's stipulated is we have to pick the first endpoint and this last endpoint. Okay, this is just the partition that I chose. With that in mind, we can figure out the length of each subinterval. Okay, the length of our first subinterval is just this right point minus this left point, so it's 1.25 minus 1. That means this interval has a length of 0.25. The length of our next interval is 1.5 minus 1.25. Again, this has a length of 0.25. The length of our next interval is a half, because 2 minus 1.5 is 1/2. This interval has a length of 0.4. And then this last interval has a length of 0.65. No, 0.85. Sorry, 0.85. And that's because 3.25 minus 2.4 is 0.85. Okay. With that in mind, that means that the norm of our partition, remember what a norm is just the length of the largest subinterval. The norm of our partition is 0.85 because it's the length of this largest subinterval. Okay, so we figured out our partition points. Let's now figure out our sample points. How do we figure out sample points? What are sample points again? Remember, sample points is just a list of points, okay, C1 through Cn, where each sample point is within a particular partition. So our first sample point has to lie within this first partition. And it can be the endpoints if we wanted to. So I could choose it to be 1 or 1.25. What I'm instead going to do is I'm going to pick this to be our sample point here at 1.2. Again, I can choose any point between x equals 1 and x equals 1.25. I'm just going to choose x equals 1.2. Okay, I'm then going to pick another sample point between 1.25 and 1.5. I can pick any number between there. I'm going to pick 1.5. So 1.5 is both a partition point and a sample point. My next sample point has to lie within this interval from 1.5 to 2. I'll pick 1.7, so that's this one here. Our next sample point has to lie within this subinterval. I'll pick 2.2. And then lastly, my last sample point has to lie between x equals 2.4 and x equals 3.25. I'll pick x equals 3.1. Okay, that's partition and sample points. Okay, hopefully that makes sense. The question now is, what do we do with our sample points once we have those? So, given a function f, a partition P, and a set of sample points C, what we do is we make a rectangle on each subinterval, and the base length of the rectangle will be the length of the subinterval. The height of the rectangle will be the height of the function at our sample point in the subinterval. So if you remember, again, back in the past, we were doing a very similar process. We were just constructing a bunch of rectangles back in the day in section 5.1, and all the base lengths were the same, and the height, we would either use the right endpoint, or we would use the midpoint, or we would use the left endpoint. We're doing something really similar here, except the base lengths aren't all the same. We get to choose the base lengths, and instead of just being forced to use right endpoint for everything, or midpoint for everything, or left endpoint for everything, we can pick any point in our subinterval. Okay, once we have our sample points and our partition points, we're going to construct a rectangle whose height is f of ci. So what happens when we plug our sample point into the function? And the base length is going to be the length of the interval that we're concerned about. We're going to get these multiple rectangles. Okay, so what does that look like here? So let me zoom out just a tad. We've got our function here. we've got our partition points, those are these blue X's here. And in each subinterval, we have our sample points. Those are our orange dots. So essentially what we're going to do is from each sample point, we're going to draw a line vertically up. So here I have these orange lines that go vertically up or down to meet the function. Okay, so here at like 1.2, we draw a line to 1.2 f of 1.2. So just where 1.2 x equals 1.2 falls on this given function. And once we do that, what we're going to do is we're going to make some rectangles. So here what I have is a rectangle whose base length is the length of our first subinterval. Remember, we got to choose this base length, and the height of this rectangle is the height of the function f at our given sample point. All right, so we get to choose this sample point at x equals 1.2. We go up to the function. This is the height of our rectangle, and the length of our rectangle is just the length of our subinterval. Okay, again, our next rectangle has the height of our chosen sample point, which was x equals 1.5. We go to our chosen sample point. We go up to meet the function. That's the height of our rectangle. The length of the rectangle is just the length of our partition that we got to choose. Our next partition is from 1.5 to 2. So we're going to draw a rectangle whose length is 1/2. And the height of the rectangle is f of 1.7. We get to make this rectangle here. Our next partition is from 2 to 2.5. Sorry, 2 to 2.4. We chose 2.2 as our sample point. So we're going to draw a rectangle whose base length is 0.4, so from 2 to 2.4, and whose height is this value here, f of 2.2, f of our sample point. And that looks something like this. Okay, so we're just drawing these rectangles. And then lastly, our last partition goes from 2.4 to 3.25. Our chosen sample point is 3.1. So the height of this rectangle is going to be minus, the height of this rectangle is going to be minus 0.961. It'll be a negative height. Okay? And the base length will be from 2.5 to 3.25. Or 2.4, I mean, sorry. From 2.4 to 3.25. So we get this rectangle. Notice this rectangle, I have it a different color. I have it in red instead of purple. And that's because we consider area under the x-axis to be negative. Okay, what we're doing is we're computing the signed area. When I say signed, I just mean it can be positive or negative. Okay, for each rectangle, we can compute the area relatively easily. So this first rectangle, I called its area A1. All it is f of 1.2. Remember that we get 1.2 because that's a sample point that we chose. We chose 1.2, so the height of this rectangle is f of 1.2. Is the height. The base length of our rectangle is just the length of our partition. So it's 1.25 minus 1. Okay, and that gives us an area of 0.648. Our next rectangle has height of f of 1.5. 1.5 because we chose that to be our sample point. Okay, and we also chose that the length of the rectangle is 1.5 minus 1.25. So here we're just calculating the area. It's the height of the function at our chosen sample point times the length of our partition of that particular subinterval that we got to choose. And this gives us our area of this second rectangle, which I've called A2. A3, which is this third rectangle here, the area of this third rectangle is the length of this subinterval, the length of the subinterval kind of on which it rests. So it rests on the interval from 2 to 1.5. So the length of this base is 1/2. The height of this rectangle is the height of the function at our chosen sample point. We chose our sample point at 1.7. f of 1.7 is the height of our rectangle. height times width gives us the area of this rectangle. For A4, so that's this rectangle here that I'm shading and unshading, the height of this rectangle is just f of 2.2, 2.2 because that's the sample point that we picked. And then the length of this rectangle is 2.4 minus 2. So that's the right endpoint of the interval minus the left endpoint. And that gives us this area. And then lastly, A5, this red rectangle, which I'm shading and unshading right here, has a height of f of 3.1, 3.1 because that's the sample point that we chose, which is notably a negative number, right? It has a negative height. It's minus 9.61. Okay, but that's totally okay to have a negative height in this kind of case. And the length of this rectangle, the base length, is of course just the length of the subinterval that we got to choose for the partition. The total area under the curve based on this estimate, based on this partition and sample points, we can find by just adding our areas together. We get 4.1022. So if we add the area of this leftmost rectangle, if we add the area of this rectangle, plus the area of this rectangle, plus this rectangle's area, plus this rectangle's area, plus this rectangle's area, which again is negative, we get 4.1022. Okay, that is how partitions and sample points work. What we're doing here is called the definite integral. The definite integral is just the area under the curve. Okay, so to reiterate, for each rectangle, we can calculate its signed area, which is f of ci, that's the height of the function at our chosen sample point, times delta xi, which is just the length of the subinterval. The Riemann sum is what we get when we add all of these signed areas together. So it's f of c1 delta x1, so that's the area of the first rectangle, plus f of c2 delta x2, that's the area of the second rectangle, plus dot 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 f of, this should say cn x, delta xn, my apologies. I don't know why it says v. And we call this signed area the Riemann sum, and we denote it r of fpc. So it's the Riemann sum of our function, partition, and sample points. Okay, here I have calculate RFPC for minus x cubed plus 3x squared on this interval given these partition points and these sample points. That's what we just saw. Okay, so if we want to calculate RFPC, just to reiterate, what we do is we break this interval into the multiple subintervals given by these partition points. For each of those subintervals, we pick a sample point. In this case, the sample points are given to us. And then we can calculate the area of those rectangles, whose height is f of our different sample points, and whose base length is the length of the subintervals. Okay, so that's the problem that's written here on screen is exactly what we just did here. Okay, let's take a look at a different example. Let's calculate f of RPC. Sorry, that should be r of fpc. So that is calculate the Riemann sum of the given function, which is 2 sine x, over this interval with these partition points and these sample points in the partition. So let's say we don't have access to Desmos, we can't draw a graph. Can we still calculate this signed area? Can we calculate this Riemann sum? And the answer is yes. So given these partition points, what we have is a bunch of different subintervals. So we have one subinterval that starts at our 0th partition point, x is 0, which is 0 in this case, and ends at our next partition point. So we have one subinterval that goes from 0 to pi over 2. We have another subinterval that goes from pi over 2 to pi. We have another subinterval that starts at this endpoint and ends at this endpoint. So it goes from pi to 5 pi over 4. And then lastly, our last subinterval starts at 5 pi over 4 and ends at 3 pi over 2. So for given partition points, we just lay them out in order and use those to make our different subintervals. In each partition, or in each subinterval here, we're given a sample point. So in this first subinterval here from 0 to pi over 2, we're given a sample point that's pi over 3. In this second subinterval, we're given a sample point that's 3 pi over 4. In this guy here, we're given the sample point 7 pi over 6. And then lastly, here we're given 4 pi over 3. And with this, we can calculate the area of these rectangles, right? What does this represent? This subinterval and this sample point, this gives us a rectangle. This gives us a rectangle whose height is f of pi over 3, and whose base length, whose distance, is the right endpoint minus the left endpoint. Okay. Similarly, this also gives us a rectangle. The base length of the rectangle is the right endpoint minus the left endpoint, and the height of the rectangle is f of 3 pi over 4. So we're going to plug 3 pi over 4 into our given function. That tells us the height of the rectangle. And then the length of the rectangle is the right endpoint minus the left endpoint. Okay. This third subinterval and sample point gives us another rectangle. The height of this rectangle is f of 7 pi over 6. And the distance, the base length, is this right endpoint of the interval, 5 pi over 4, minus the left endpoint. And then lastly, this subinterval and this sample point gives us another rectangle with height 4 pi over 3 and length 3 pi over 2 minus 5 pi over 4. Okay, and now we can compute these easily enough. Remember that our given function is 2 sine x. So here on this first rectangle that we're dealing with, this first subinterval and first sample point, the height is 2 times sine of pi over 3. And then the length is pi over 2. Sine of pi thirds is 1/2. We multiply by 2, we get 1 times pi over 2. Gives us pi over 2. So that means this first rectangle, whose base is this subinterval, and whose height is f of pi thirds, this rectangle has an area of pi over 2. Okay, similarly, this next rectangle has a height of f of 3 pi over 4, so that's 2 sine 3 pi over 4, and the length of this rectangle is pi minus pi over 2, which is pi over 2. Sine of 3 pi over 4 is root 2 over 2. We multiply by 2, we get square root of 2. So we get square root of 2 times pi over 2, which doesn't have really a nice simple way to rewrite it. Okay, but this square root of 2 times pi over 2, this is the area of this rectangle. And the fact that this is positive tells us that this rectangle here lies above the x-axis. Okay, remember, because we're dealing with signed area, so if things are above the x-axis, they have a positive area. If they're below the x-axis, they have a negative area. What about this second to last partition? Well, the height is f of 7 pi over 6, so that's 2 sine 7 pi over 6 times. And then what is this distance here? What's 5 pi over 4 minus pi? That's just pi over 4. Sine of 7 pi over 6 is square root 3 over 2, negative square root 3 over 2. So we multiply that by 2, we get negative root 3 times pi over 4. And then lastly, this last interval and sample point, f of 4 pi over 3, that's 2 sine 4 pi over 3. And so, and we multiply by 3 pi over 2 minus 5 pi over 4. That's going to be pi over 4. 2 times sine of 4 pi over 3. The sine of 4 pi over 3 is 1/2. So we multiply by 2, we get 1 times pi over 4. And I'm pausing here because I think I may have remembered my unit circle wrong. And I think this might be wrong, this might be wrong, and this might be wrong. So please double check me on that. In fact, I'll double check myself right quick. Let me open a calculator. So we want the sine of pi over 3, and we want to make sure that we are in radians. Well, that's certainly not, that's square root of 3 over 2, isn't it? 3 over 2. Okay, so I apologize. I got my unit circle wrong. What that means is that this should be square root of 3 this should be minus 1, and then this should be square root of 3 as well. That should be minus square root of 3. Okay, sorry about that. That's all been fixed. What we did, let's recall all we did, despite the fact that I got my signs, my unit circle wrong. We were given a set of partition points, and what we did is we just took 2 partition points at a time and made an interval. In each interval, we were given a sample point. And then with that information, we were able to calculate the area of some rectangles. Okay? The height of each rectangle was f of our given sample point, and the length of the rectangles, like the base length, is just the length of the interval. And we were able to go through and compute the area of these different rectangles. And now we can add them together, and that will give us everything we want. So we can just add root 3 pi over 2 plus root 2 pi over 2 minus pi over 4 minus root 3 pi over 4. And I'm happy if we just leave it like this. Instead of trying, we can go through and get a common denominator, but for now we can just leave it like this. Okay, that is how Riemann sums work. Okay, we're given a partition, we're given sample points, we just build some rectangles, we calculate their area. Okay, let me introduce some more definitions. I'm not sure why this is so stretched out, but here we go. And there should also be an A here. The definite integral of f over ab, denoted by the integral sign, is just the limit of Riemann sums as the partition goes to 0. Let me unstretch this out a bit, because that looks just not great. Oh, there was an A there the whole time. Look at that. Okay. The definite integral of f over ab, and that looks like this. This here is the definite integral. We've seen this integral symbol before. Now we are just given endpoints from an interval ab. Okay? All we do to compute this is we take the limit of our Riemann sums as the norm of our partition goes to 0. What's the norm of our partition again? Remember, it's just the largest subinterval. So actually, with that in mind, let's take a look back at this question, where we're supposed to calculate the Riemann sum of this function with these partition points. What's the norm of this partition? Well, the norm, of course, is the length of the largest subinterval. What are the lengths again? So this subinterval has a length of pi over 2. This subinterval has a length of pi over 2. This subinterval has a length of pi over 4. And this subinterval also has a length of pi over 4. So our norm, the norm of our partition, is the largest of those lengths, which is pi over 2. Okay, as the partitions get smaller, the area, like our approximation, gets better and better. Okay, and if we take the limit as the norms of the partitions go to 0, what we're going to get is the definite integral of f over ab, which is just the signed area under the curve. When this limit exists, this limit, also this limit, because these are the same thing. When the limit exists, we say that f is integrable over the interval ab. The process of computing integrals is called integration. The function f of x is called the integrand, and the endpoints of our given interval ab are called the limits of integration. Okay, and one thing to note that I kind of mentioned in class on Monday, we can use any variable we want to. So like this integral from 0 to pi of sine x dx is the same as the integral from 0 to pi of sine t dt is the same as the integral from 0 to pi of sine u du. These are just different variable names. They're all the same. Now you might think, how often is a function integrable? It seems kind of like this really random arbitrary thing of drawing rectangles and whatnot. Well, fun fact, if f is continuous on a given interval, except at finitely many jump discontinuities, it has to be jump discontinuities. Okay? If they are discontinuities at infinity or removable discontinuities, then we might not have that f is integrable over ab. Okay? So again, if the function is continuous on ab except at finitely many jump discontinuities, then f is integrable over ab. And then one more definition just to reiterate, the signed area between the graph of f and the x-axis over a given interval is this integral here that we're computing. This integral here that we're computing computes signed area. Okay? And so just to reiterate, for this given curve here, this area is considered positive because it's above the x-axis. This area is considered negative because it's below the x-axis. Okay, and I've got a couple more definitions and whatnot, or just ideas, right? How do we actually compute integrals of functions like sine x? We'll get to that because, believe me, we don't compute it by actually taking finer partitions. Okay, we compute it with antiderivatives. We'll talk more about that on Wednesday. For now, it suffices to find area geometrically. Okay, what do I mean by that? Well, let's calculate the following. This integral from 0 to 5 of 3 minus x, and this integral from 0 to 5 of the absolute value of 3 minus x. What does this integral sign represent when we have these endpoints here? This means find the area under the curve of 3 minus x between x equals 0 and x equals 5. Oh, look at that. What a handy graph. Here I have the curve x, or f of x equals 3 minus x, and we're given that x is between 0 and 5. So we have this endpoint here and this endpoint here. And our goal is to compute the area under this curve. Notice we have two kind of different parts of this curve. We have one part here where we are above the x-axis. Let me use a different color. We have one part here where we are above the x-axis, so we have positive area. And then one part here where we are below the x-axis, so we have negative area. Okay. But we can compute the area of these two triangles relatively easily because we know that area of a triangle is 1/2 base times height. And remember, the actual area under this curve is this integral here. So we get two kind of different triangles that we need to find the area of. Let's find the area of this first triangle. The height is 3. The height is 3. The base length is 3. So this triangle has an area of 9/2. For this triangle, this base length is 2. And then this height of the triangle is -2. So we get 1/2 of -4 equals -2. So the area of this triangle, the area under the curve from 0 to 3, is positive 9/2. The area under the curve from 3 to 5 is -2. So our total area is 9/2 minus 2, which is 5/2. So that means that this integral here is 5/2, the area under the curve of this given curve. Okay, how can we find this guy, the area from the area under the curve of absolute value 3 minus x from 0 to 5? Well, we apply a very similar thing. Here I have the function drawn. You'll notice we get two triangles again. And this time, both areas, the area of both triangles, is positive, because both triangles lie entirely above the x-axis. And so we can compute the area of both triangles relatively easily. The area of this left triangle is 9/2. The area of this right-hand triangle is positive 2. And so the total area is 9/2 plus 2, which is 13/2. So that means that this integral works out to be 13/2. Definite integrals are area. They are the same thing. The definite integral of this function is the area under the curve between these two endpoints. For this section, there's only one or two problems where you have to actually lay down partition points and sample points and whatnot. The vast majority of the homework in this section is computing area, and it's mostly through geometry. There's not much calculus involved. Okay, but with that in mind, let me talk about a couple of properties of integrals that are going to be really helpful. One, if we have a definite integral, remember a definite integral means we have these endpoints here. If we have a definite integral of two functions, so the integral of f of x plus g of x, that breaks apart into two different integrals, an integral from a to b of f plus the integral from a to b of g. Okay, also if k is a constant and we want to find the area under the curve of k times f of x, well, that's the same as k times the area under the curve of f of x. Okay, this one's kind of weird, but if we flip the bounds of integration, right? So here we're taking an integral from a to b of f of x. If instead we take an integral from b to a of f of x, we flip from positive to negative, or vice versa. So let me rephrase that. The integral from a to b of f of x dx is negative the integral from b to a of f of x dx. This does not come up very often, but it can come up. So we need to throw that out there. And then lastly, the integral from a to b of f of x plus the integral from b to c is the same as the integral from a to c. And this makes total sense, right? If we have some function, we have our points a, b, and c. Well, the area under the curve here is the integral from a to b. The area under the curve here is the integral from b to c. If we add those together, we get the entirety of the area under the curve from A to C. So with that in mind, here's a little problem. Let's say we're given that the integral from 1 to 4 of f of x is 2, and the integral from 1 to 4 of g of x is 6. Can we compute the integral from 1 to 4 of 3f of x plus 1/2 g of x? And yeah, we totally can. We can just use the things that we just learned, right? This guy we can rewrite as the integral from 1 to 4 of 3f of x dx plus the integral from 1 to 4 of 1/2 g of x dx. And now we can factor out these constants here. So this is 3 times the integral of 1 to 4 f of x dx plus 1/2 the integral from 1 to 4 of g of x dx. And we were told that the integral from 1 to 4 of f of x is 2, and that the integral from 1 to 4 of g of x is 6. So this gives us 3 times 2 plus 1/2 times 6, which is 6 plus 3 equals 9. Okay, so this is just using properties of integrals to solve a slightly more complicated function, or the integral of a slightly more complicated function. And that's it. That is section 5.2. This first part here with the sample points and the partitions can be a little overwhelming. It's kind of a lot of definition thrown at you all at once. The good news is we pretty much don't have to worry about it. We're going to learn how to not use these and how to compute integrals in a much easier way, and in a much more general way than being forced to just use geometry. But for now, when you're asked to find a definite integral, that means you're asked to find area under a curve, you're going to use geometry to do it. You're going to use your knowledge about how to find areas of circles or how to find areas of triangles or rectangles to find area under a curve. We're going to get to a much more general, just kind of better way on Wednesday. Thank you so much for watching.